Welcome, everybody, to another installment of our Quantum Software Talk series. My name is Dr. Sarah Kaiser, and I am super excited to have with us today Loïc Henriet, who works on a really cool kind of pulse-level project for controlling neutral atoms. A little bit of background about Loïc. He holds an engineering degree and a PhD in theoretical physics from École Polytechnique in France. He subsequently worked as a researcher at the Institute for Photonic Sciences in Barcelona, Spain. I guess there are other Barcelonas. His research interests lie in describing the collective effects of light matter systems. And in June 2019, he joined Pascal, a Paris-based quantum computing startup manufacturing quantum processors powered by arrays of single atoms. Since then, he has been heading up the quantum software development efforts there at Pulsar. Pulsar? Is it Pulsar or Pulsar? Okay. Sounds good. So let me switch over and bring Loïc in. How you doing?
Hi.
Can people hear Loïc all right? I've done this a couple times where I've launched into stuff and people couldn't hear the guest.
Okay, so thanks a lot for having me. So it seems that it's working. Okay, I will.
Looks like it.
Thanks a lot for the invitation. I will talk to you about Pulsar today, which is a library for the design and the simulation of pulse sequences for neutral atom quantum devices. So before diving into Pulsar, let me talk briefly about how neutral atom quantum processors work in a nutshell. So in such devices, qubits are individual neutral atoms, and those atoms are trapped in arrays of optical tweezers, which are basically traps for just single individual atoms. And as you can see here on this plot, from the device, each green dot corresponds to one unique rubidium atom that is held fixed in space, in 1D, 2D, or even 3D geometries. So we can have up to a few hundred qubits in arbitrary shapes. And we should be able to reach several thousands of qubits with the exact same technology building blocks. So it's a really scalable technology. And so I told you that our qubits are atoms. The quantum information itself is stored in the electronic states of those atoms. In other words, the 0 and 1 states of our qubits are two distinct electronic levels of those atoms, and the interaction or the ability to do multi-qubit gates is provided by the dipole-dipole interactions in those devices. So a little bit more detail about that. So the key idea for manipulating quantum information is that we will be using high-lying states that are called Reedberg states. And the particularity of those states is that they exhibit a very large dipole moment, which means that they can interact over very long distances. So for example, more specifically, you can reach interaction scales of the order of the megahertz for two atoms that are spaced by already a few micrometers. And the first proposals were in the early 2000s, but the first experiments were like 1 decade later at the Institut d'Optique Graduate School near Paris, and also in the US in the group of Safman and Lukin. So it allows us to do many things. The first field of application is to have complex Hamiltonians and pilot the device in analog mode. And the other one is to do standard quantum computing with high fidelity quantum gates. So the main field of application of those devices have been so far quantum simulation, where you recreate in the lab quantum model of interest for scientific discovery. And there have been many landmark experiments with this technology. I listed a few of the great papers here, with the bold ones from the IOGS group near Paris, from which our company Pascal spun out. So it's interesting to note that those experiments already operate in a regime where classical computers cannot explore, even with state-of-the-art methods like tensor networks or things like this. And in particular, the papers published in 2021 here investigated the quantum magnetism, of which I show an illustration here, corresponding to the description of how interacting spins behave at very low temperatures. And they did that for more than 200 spins. So another emerging field where you could use those devices is to try to solve hard computational problems for which classical methods are not super efficient. For example, solving optimization problems or accelerating machine learning procedures thanks to quantum effects. So I illustrated here one particular example of an optimization problem called the maximum independent set that neutral atom devices can solve rather natively. So an independent set of a graph is a subset of vertices such that no pair is connected by an edge. So you can see here on this example that the red dots are never connected by edges. And finding the largest of such subsets, the largest independent set, is a NP-complete problem. So here, it's super easy on this particular example. The maximum independent set corresponds to the two graphs here in the middle, where you have only four atoms, four nodes. But in general, for arbitrary large graphs, it's super hard to find the maximum independent set with classical methods.
So, quick question about that.
Yeah.
I'm curious. So you mentioned, I'm going to ask two questions. You said that neutral atoms are particularly good at solving this problem. So, like, what about the systems makes that true? And what is there like an application or kind of like use case for this particular hard computational problem?
Yeah. Okay. Well, thanks for those questions. So I will come back to this particular example later in the discussion. The idea is that as you saw earlier, we can place our atoms in arbitrary shapes, and it allows us to engineer some graph structures arbitrarily on the processor. Like the atoms are the nodes of the graph, correspond to the node of the graph. So by rearranging your register, you can study one particular graph or another one super easily. So that's the good feature about our processor. The register is not manufactured and built. It's really something that you can reconfigure. The geometry can change, so you can really implement one graph or another one. And we'll see later on that actually one of the Hamiltonians that we can engineer corresponds to the cost function of this problem exactly. So you can implement like QAOA type algorithm natively.
Oh, that's
so
super nice.
That's yeah, that's quite cool. And that's the first one of the first natural use cases with those devices for optimization problems. And in this paper here that we just published, it has been published 2 days ago, I think. We studied a use case with the EDF, the French utility, where solving this problem corresponds to optimizing the charging schedule of a fleet of electrical vehicles. So you have electric vehicles that need to charge on a finite set of charging stations, and you have constraints, and you can actually reformulate this problem under the form of a maximum independent set problem. So that's one first use case that we studied together with the people at EDF. But I think there are many other examples where you could map some scheduling problems onto this particular graph problem. So yeah, I invite you to look at this paper for details about this particular implementation, but I think there will be other ones.
Yeah, I'll try to drop a link to that in the chat. Quancha also asks what encoding is happening here. So maybe that's...
Yeah.
Yeah.
So the idea here that we have each atom has many electronic levels, and you isolate two of them and say, okay, this is my 0, this is my 1, and then the Hamiltonian that governs the dynamics of the system depends on those levels that you choose, and you can do various things with that. Either you're interested in the Hamiltonian itself, its properties, or you try to devise gates based on that. So you can choose various levels and do various things. So there is no one answer to that question. But yeah, that's a quite rich structure of the of the atoms that gives rise to many interesting things that you can do. But as you can see here, the key element to control the quantum information is really the laser light that couples one level with another one. And by controlling the lasers, you can do all of this that I described. And that's what Pulsar is all about. It's controlling the timings and the scheduling of the laser pulses on the device so that it achieves what you want to do. So it's a very low level quantum software library, but it's very low level and hard to get into at first, but it's also very powerful because you can have various encodings by doing that.
Sweet. Thanks everybody for the questions, and thanks for the great answers there.
So that's great because that actually gets me to the next slide, which is about Pulsar itself. So it's an open source library for controlling neutral atom devices at the pulse level. So it's a rather low level, requires some work, but at the same time very powerful, as I just said. And the idea is that it gives you control over all the relevant physical parameters of a neutral atom experiment. And one important thing is that it's free of the computing paradigm, either analog Hamiltonian evolutions or digital gates. If you can do it on a neutral atom device, then you can do it with Pulsar. Due to the language being very low level, it keeps the user in close contact with the hardware features and constraints, and we hope that people will contribute to designing smart protocols for manipulating quantum information or come up with new gates, for example, or things like that. So it's really low level, close contact with the hardware, but it can enable the creation of new interesting schemes. And so finally, it also features a classical emulator for testing and experimenting pulse sequences, and it's based on the great open source Python library Qtip. And so the idea is that with Pulsar, you can either send your sequences to a real quantum hardware or use it with an emulator, simulator, classical simulator, either locally on your laptop or on a server if you want some more computing power. So okay, so let's dive into the structure of Pulsar with a few more slides. And then we'll look at some examples. Okay, so in Pulsar, we start with a register that the user can create. So in other words, anyone can choose specific positions for the atoms. You can yourself define the geometry of your register. And then we have our channels, and channels are basically lasers. So these lasers can be either global in the sense that they act on all the atoms of the register at the same time, or they can be local and target specific subset of the atoms. And all of these forms what we call a device. And depending on the specific hardware on which you'll send your pulse sequence, there will be some constraints associated with the register and the channel. So, for example, each hardware processor has a specific set of available channels, and there might be some constraints on the maximum number of atoms that you can put on your register, the minimal distance between atoms, or the maximal distance between atoms. So there are some constraints, the finite number of channels, and you cannot do anything you like with the positions of the atoms. And then the idea is to fill these channels with pulses, so laser pulses. So each one of this lane here corresponds to a channel, and for each channel you add pulses. So a pulse is composed of an amplitude waveform, which modulates the Rabi amplitude of your laser in time. Here it's shown in green. You have also a detuning waveform that modulates the frequency of your laser in time and a fixed phase. So all of this uniquely describes the state of your laser at a given point. So it's all you need to control your laser.
Question about
so
that.
once you have, yeah.
So yeah, you have this abstract model of the device, which you mentioned has some physical constraints. How do you actually go and, like in real life, if you're using the package here, do you need something else like, Pi serial, or how do you actually go about taking these pulses and controlling the hardware? Or is that something separate?
So right now it's not coupled to our real devices. So you only have the simulation parts that are available, but we will build an interface, and you will only have to send your pulse sequence to our public API, and it will be possible to run on the hardware. But the things that the specs of our devices are public. You can access it directly in Pulsar. So everything is already built in. You know what is the minimal distance between atoms that you can have. For example, if you want to send a pulse sequence on our device at Pascal. And the idea is that for each real hardware, you have all those specs that are publicly available directly in Pulsar.
Gotcha. And, so basically all of the nitty gritty of actually like AWGs and whatever that needs to consume the pulses and control the lasers is kind of behind the API, so you don't have to worry about it.
Exactly. Gotcha. So once you create your sequence, you can either send it to the emulator or to an AWG, and that's the thing.
Gotcha. Sorry, I asked because I've spent a lot of time trying to automate laser controls from Python. So when I did my experimental stuff, so I was just kind of curious about the details there.
Yeah, sure. No, that's a great question, and the objective is that we really have one unique framework to pilot the device and also to simulate it, so that the emulator is really something that is supposed to very faithfully reproduce the behavior of the device, so that it helps us to characterize it and for development.
It's also a lot cheaper to run an emulator than it is to run on hardware.
Obviously, yeah, that's correct. So now that you have your sequence, it will be just running sequentially in time. So for example, here you start here at the beginning, and what happens first is this channel, which is a local channel, and it will act on the qubit number 4, so which, for example, is this one. Then you have something on the global channel, so Redback global here, which addresses all the qubits at the same time. So you have here the global laser shining on all the atoms. And of course, if you have different channels that are not conflicting, so for example, here one channel acting on qubit 1, and here another local one acting on qubit 0, well, you can have some parallelism, and it allows you to drive 2 qubits at the same time. And there is also some retargeting. So that's one key difference with respect to pulse level languages for superconducting qubits, for example, where one channel is associated with 1 qubit. Here, one channel is one laser. So the laser can point to a specific qubit or to another one, and you can retarget it in the duration of your sequence. So one channel is really a laser, and you can change the qubit it points to. So here it points to qubit 4, and then it does some pulse here. So that's how it works. So I should show you a particular example, and now I think it's a good time to start doing it with a demo. So we'll change the screen and go here. Sorry about that. All right.
Yeah, and if you can zoom in the text a little bit, that would be. It may be uncomfortably large for you, and I'm sorry, but it just makes it easier for folks to read here.
Is it better now?
Yeah, I think that's pretty good. Chat, if you want it larger, just let us know.
All right, it's already quite big for me, but I can make an effort. All right. So it's a standard Python library, so you can pip install it. And then, so at startup, you need to load some packages. Okay, so let's start here. So the idea is that you can create your register by providing an NumPy array with coordinates in micrometers. So, for example, here I define an NumPy array with my 5 qubits here, and I can build a register from those coordinates directly. So you have the feature that you can draw your register where it shows the positions of your atoms in 2D, where the position is in a micrometer. So once you have a register, you can start building your sequence. So a sequence, to build the sequence, you have to provide a register and a device. So a specific device. So Shadok2 is the name of our device. Well, it's its name. Don't ask why. But so you can once you have that, you can just instantiate your sequence with the register and the name of the device. So device is something that you can import directly from pulsar.devices. So as I said earlier, it includes all the constraints that are related to that device. So for example, if I do something like I change the position of this qubit to be 0, 1, so you see that here the 2 qubits are very close, and if I try to start a new sequence, it will throw an error because the qubit positions don't respect the minimal distance between atoms for this particular device. And the minimal distance here for our devices is 4 micrometers between qubits. So here you see that it will already throw an error if it's not possible to have this particular register with this device. All right. So it will also throw an error if you put here too many atoms, and the hardware cannot have as many atoms as you want, or if the distance between 2 atoms is too large. So we have typically 100 micrometers maximal distance between 2 atoms.
And so, those would be the those would be the parameters you could find publicly available, like on your website or something like that for the devices, right?
Yeah, exactly, and it's also in the pulsar.devices classes. You can have a look at them, like what are the So it's cool. It's here already. Like Shadok2, you have all the specs that are shown here.
Gotcha. Sweet.
Yeah, and So what you can do also, so once you have you have instantiated your sequence on a given device and with a register, So now it's time to build something. So the first thing is that you can look at what are the available channels on your the available channels on this particular device. So you see that you have 3 particular channels, Reedberg global or local or Raman local. Okay, so it gives you what are the possible things, what are the possible lasers that are plugged in. So let's, for example, I will use only one channel here, which will be the Reedberg global. So I will call it channel 0. Okay. So I declare my channel. It means that I will be using it for the sequence. So I will be using this laser for the sequence that I will create. So now is the time to so you have your sequence, you declare the channel, and now it's time to fill in pulses inside your channel. So to create a pulse, you can just use like some built-in method, like for example constant pulse, which with the duration in nanoseconds of 1,000 nanoseconds, so 1 microsecond, an amplitude of 1 megahertz, a detuning of 0, and a phase of 0. See, so this is the order of the arguments here. You can create your pulse, and then from there you add your pulses to your sequence. So you add pulse 1 on channel 0. And so there is a, oops, what happened here? Okay. So you can actually draw your sequence to see how it looks like. So usually it's not that long to, but I think like having Skype on makes my computer kind of slow. So here you have a pictorial representation of what you did. So basically on channel 0, you have 1 pulse. So here I think I added this guy twice because the pulse here lasts 2 microseconds. So it corresponds to having a particular value of omega and a particular value of delta in time. So here's an example of very, very simple pulse that you can have. So as you said, as you saw, there are many built-in methods for pulses, because you can want to use constant pulses or ramp pulses, for example. So that's something that is that can be useful to have some built-in waveforms for your pulse. So I think, did I import here? Yeah, so for example, I can have a ramp waveform that I import. And yeah, there are some other built-in waveform like the Blackman waveform, if some of you know what it is. It's a particular shape of a pulse. And then you can build your waveform like this. So Blackman waveform, it's characterized by its duration. So yeah, I'll choose 1 microsecond, and by its area. So here you can say, for example, pi. And once you have your waveform, you can it can be used to modulate the detuning or the amplitude of your pulse. So you can also draw a waveform. It's really something very simple, like the value with respect to time. So here is what a Blackman waveform looks like. And then you can build a pulse from a waveform. So for example, I'll take a constant detuning wave pulse, but this time my radio frequency will be given by the waveform that I just created, which is a Blackman waveform, a detuning of 20 and a phase of 0. And then you have your your pulse that will look like this. So here you have a detuning here of 20 radian per microsecond and a Rabi frequency which looks like this, a Blackman waveform. So okay, you can do various things like that. You build really at the pulse level everything. You can also provide the pulses with the arbitrary waveforms. Some interesting thing is that, so as I told you, the device knows about the constraints of the hardware. So sometimes you might want to build a pulse that is not feasible on the hardware. So for example, here, let's say I want to use a very powerful laser with a huge Rabi frequency. Then I add it to my sequence, and it will throw an error as well, because the pulse amplitude goes over the maximum value allowed for the chosen channel. So it's also included in this object here from that you import from devices. All the specs in terms of geometry, laser that you can have on the system, like everything is here. And when you try to do something that is not allowed on the hardware, well, it shows right away. So okay, so I messed a little bit what happened here. I will study now one particular example, more useful than just some random pulses, but corresponding to solving the problem that I was talking about, the maximum independent set with neutral atoms. So if you have questions about how it works to build pulses and do stuff like this, maybe it's time to do that. And if you don't, I will jump directly to the application, which is solving this graph problem that I told you about in the beginning of the presentation.
Yeah, so I think I've got a couple questions here. So I think an easy one is just, is the Blackman distribution, is that just like a Gaussian parameterized a certain way, or is it actually a different expression?
Yeah, it's not really a Gaussian, but like something like, which I don't know what it looks like exactly, but you can like this Blackman function is like this.
I'm just trying to see if there's other names that I might know it by.
Yeah. The important thing is that it's quite useful when you want to really don't have many parasitic frequencies in your signal.
Gotcha.
And that's super useful for real experiments actually.
Gotcha.
Yeah.
Zero Dynamics is asking, how does one access the underlying Hamiltonian?
Yeah, that's a very good question. So it depends on the levels that you are targeting, and for those levels that will be so for the Reedberg, those levels that I chose here, it corresponds to Ising Hamiltonian that you can have a look here in the docs of Pulsar. So quantum computing neutral atoms here.
I also put a link to the docs in chat for folks.
Yeah. So here you have so you can choose various levels, but for the ones I am working with today, the Hamiltonian that governs the dynamics is this one. So you have your lasers that control single body terms like sigma x with the Rabi frequency, sigma z with the detuning, and then you have an interaction that really looks like an Ising interaction. The n is sigma z plus 1/2, this operator. So really, like this term is a zz interaction term. So this guy really looks like a transverse field Ising Hamiltonian. There are other kinds of Hamiltonians that you can engineer, depending on the levels that you choose. But right now, this is the most common one, let's say, and the one that I will be using for the application. But yeah, that's a very good question. The Hamiltonian that you have depends on the levels that you choose. So here, if you choose the ground Reedberg, as I did, this is the Hamiltonian that you end up with. So that's
I don't
very
know.
good question for, yeah.
I don't know if this is a feature or not yet, but like, is there a way, given the levels that you've chosen, for it to just print out the Hamiltonian that corresponds to, or?
That's a good point. So right now we don't have we have only one configuration for this one, but I guess in the future that would be super helpful to have this feature. It's not yet done, but yeah, that's a very good point.
Someone in chat go file that as an issue.
Yeah, exactly. Yeah, feel free to do that. So by the way, here is our repo, and so many issues already, but you can don't hesitate to find an issue, of course.
I also put a link to the repo in chat, so you can find
Yeah.
it. You can easily click on it there.
That's perfect. And so you can see some of them are tied with the unitary hack. So good opportunity to participate to this beautiful event.
You have a chance for both the cash prize bounties for participating, and also all kinds of digital swag and a drawing for real physical swag. So plus there's all kinds of nice folks like Loïc and people on the Discord to help you out if you have questions and stuff, because I know doing open source stuff, if you're a scientist, that can be kind of intimidating, and if you're a developer, doing the quantum stuff can be intimidating, so we got you.
Right, so back to the use case. So it concerns the resolution of the miss problem on the graph that I talked to you about previously. And the key idea is based on an effect called the Redback blockade effect, which prevents two atoms that are close together to be excited to a Reedberg level at the same time. So how does that work? It's summarized here on this plot. I'm showing here the energy of the levels with respect to the distance between the two atoms, for two atoms. So at large distances here, the two atoms basically don't interact, and you can excite two of them in the Reedberg state at the same time. Having the two atoms excited costs exactly twice the energy of having one atom excited. So by driving the atoms with a laser, with a resonant frequency that matches the energy difference between the two levels, then you can excite the two atoms at the same time. But on the contrary, here at small distances, there will be a strong dipole-dipole interactions. A strong dipole-dipole interaction between the two atoms. And this will offset the energy of the doubly excited state. And as a result, a resonant laser will be able to bring the two atoms from the 0-0 state to a coherent superposition of the two atoms with one excitation, but will not be able to excite the two atoms at the same time. So this is what we call the Reedberg blockade effect. When two atoms are close together, they cannot be excited both at the same time. And the typical crossover distance between these two regimes is called the Reedberg blockade effect. So it's you have a typical length scale that gives you that separates these two regimes. Well, on this side, the atoms are independent. You can excite them, and here they are correlated, and you cannot excite them at the same time. So then you can use this effect to try to solve the maximum independent set. So how? Well, the idea is that the Reedberg blockade effect will restrict the dynamics to the independent sets of your problem. So let's see how. So the idea is quite simple. So given an input graph, for this one, for example, you start by reproducing its geometry with the atoms of the register. So one atom for one node of your graph. And having an edge between two nodes in the graph here will correspond to having two atoms interacting in the chip, so within the Reedberg blockade radius of one another. So if two atoms here are within the blockade radius of one another, it means that it corresponds to an edge in the original graph. And the blockade effect will naturally penalize energetically the configurations where connected vertices are excited at the same time. And this corresponds exactly to the cost function of the maximum independent set, where you don't want to have connected the atoms excited at the same time. So you natively realize the cost function of the system with your of the problem maximum independent set with your atoms. And because you can choose the arbitrary positions of your atoms, you can do that for all the graphs in 2D that you can draw on this in this fashion. And then we can do a standard QAOA procedure to try to find the optimum. So just to recall, the QAOA procedure is a variational procedure where you apply in turn the cost Hamiltonian, so the cost function of your problem, alternating with a mixing Hamiltonian that shuffles the coherences of your atoms. So as I told you here, the interaction part of our Hamiltonian naturally realizes the cost function here HC, and you can engineer this HM by just strongly driving with a laser. And so the QAOA works that way. So you have several layers of those Hamiltonians that you apply in turn, and you try to optimize for a cost function HC here by adjusting the parameters here with a classical optimizer. So it's really something standard right now. One of the prime candidates to have some quantum speed up in the near term with the noisy devices. So that's pretty cool that we can actually natively realize this cost Hamiltonian. So it's not really costly for us to implement QAOA for this problem. So here, the following code is an example of how you would do that using Pulsar. So I will not run through everything again, but the idea is that you have the register like this. It's the same the one I showed you before. So you have your 5 atoms here. And there's an interesting feature in draw. You can provide some arguments like draw graph equals true, and draw half radius equals true, and it will on top of the positions of your atoms like you had here. Here you just had the bare positions of your atoms. What it will do is that it will superimpose the blockade radius, and if two disks intersect, it means that there is a link in the graph under consideration. So you have really like the drawing of the graph that you're studying, and you want to find the maximum independent set of this graph. So actually, the maximum independent set of this graph is of size 3, so it's super easy for this particular example. So it's atom 3, 4, and 1 excited, or 3, 4, and 2 excited at the same time. So we already know the answer by eye, but obviously with the real hardware, we will be able to have very large graphs for which it's harder to find the maximum independent set.
So,
okay, so
quick question. So if I understand the energy curves that you kind of showed above with the levels, I'm basically trying to figure out, do you want to maximize, like by the diagrams there, it looks like you want to minimize, you want them to overlap, but as small as possible, because then your constraints on the kind of precision on the laser are less, right? Or what's the driving thing that makes it so that you want them to just touch, right?
Yeah, so you actually what you want is really to be either on this side of the Redback blockade or on the other side. So because you really have a typical interaction strength, and you want them in the graph to be either connected or not connected. So the distance, the absolute value of the distance doesn't really matter. The important thing is that it's above or below the threshold. And so here, if it's below the threshold, it corresponds to having an edge between the two atoms. And here, for example, this one and this one, they are far away and they are not connected in the graph. So you want them to be closer than Redback blockade radius for atoms that are supposed to be connected, and the other way around for atoms that are not connected, for nodes that are not connected.
Cool.
So
Thanks. I think that makes sense.
So yeah, one cool feature about Pulsar is that you can build parameterized sequences. So in the examples that I showed before, you had to input some real values here for all the things in your pulse. But what you can actually do is to have parameters. So to do that, you have to use what's called the sequence builder and declare variables. But then what it will do is that it will build some signature of your sequence, and it will fill it in only at the end. So it will fill actual values only at the end. And you can have parameterized sequences like that can be super useful for QAOA algorithms, like variational algorithms, where you want the same sequence but with changing only one parameter, and you want to do that many times. And that way you don't have to create one new sequence at every time you want you have an iteration of QAOA. You can build one parameterized sequence and just change the value of the parameter. So here you see that you can build a constant pulse that has this T parameter, and here this S parameter, and you can just, in the same way you added pulses before, you can just add pulse here. So I will skip through that, and I will go directly to the end. The idea is that you can then minimize your cost function. I'm using the emulator here, of course, and not the real hardware. But the good thing that in the end you sample the states that you have, and you find that you indeed are able to sample with a rather correct probability the two maximum dependent sets of your problem. So your hardware was able to here the emulator, not the hardware, was able to find what were the two configurations that correspond to a maximum dependent set. So that was just to show you one particular example. There are many of them here in the read the docs. So this one was QAOA for the UD-MIS problem. But there are many things that you can explore. So for example, trying to do gates yourself and implement the standard protocols for gates, various things that you can do. So right now I showed you an example with the emulator, but we are currently actively developing the hardware, and this is a picture of our hardware. I will play from the current slide.
Quick question about the built-in gates. So, well, okay. So you're showing an example of how you can make your own gates. Are there some, kind of like the standard ones already available in Pulsar then?
Yeah, so it's a very good question. So right now you really have to redefine everything yourself, like the pulse sequence that builds your gate. But we are trying to build some additional layers on top of Pulsar so that you can use standard gates. And like you can say, okay, I want just a CZ standard way, and it will compile this CZ to a sequence of pulses. So we are trying to do that and to interface with other higher level software that are at the gate level. So, for example, doing something like a QTIP QIP does, like, or even being coupled to it, so that you can really build your circuit, and then it will compile it to a pulse sequence in Pulsar.
That's so cool.
That's cool.
Sweet.
And then you can explore the various things. You can change a little bit the pulses so that it's no longer the standard gate, but the one that you think is better, and then you can test. And that's the cool thing about having it very low level, is that you can understand what are the effects of what you're doing really on the hardware. And that's what we are currently doing right now in the lab. So this is a photo of our prototype, and the example that I explained, solving maximum independent set. We are currently doing it on the hardware itself, and also using Pulsar. So that now, instead of having an emulator as a backend, Pulsar is coupled to AWG and to the atoms. And we are currently studying the maximum independent set problem, and we hope to achieve a few tens of atoms on the hardware itself, which would be very hard to do on the emulator, of course. So that's the objective of Pulsar, to be really something to pilot the hardware at a very low level. So the most important slide about the credits, because it's something that has been, Pulsar is an open source initiative, but it has been started inside Pascal by Pascal team members. So we are a startup based in France, developing neutral atom quantum processors, and the two main developers of Pulsar, Enric Silverio, Sebastian Grijalva, and there are many collaborators inside Pascal that contributed. And if you want to be participating to this project, it would be super helpful to have some external views and participations. We benefited from very helpful discussions and help of Nathan Shama and Peter Karalekas at Unitary Fund when we developed the software in the past few months. So, summary, even though Sarah already pasted the links, I think, in the Twitch. So you have the GitHub repo here, Pulsar, read the docs, and we have also an archive paper that was posted last week or 2 weeks ago, something like this. So to go back to the GitHub, so you have here instructions about Pulsar itself, what it is, how you can install it, and also very importantly how you can contribute. That's super helpful if you guys have some ideas on how to extend the capabilities of the library. You have some issues that are already raised, and some of them are tagged as good first issues, and also with the unitary hack tag. And don't hesitate to participate. It's a great occasion to get into open source software for quantum computing. And I think in Pulsar we have some nice opportunities to contribute. And yeah, about the paper on the archive, because yeah, it's oops, that's not the that's the docs. So the physics of neutral atoms is not always easy to understand, but that's the purpose of this archive paper, to have some more documentation if you want to understand more about the physics, how it works, etc. You have the description of the physical system, the levels that we can address. So here, for example, the Hamiltonians that you can engineer, depending on the levels you choose. Another one that we could engineer. Some schemes for gates. So this is, for example, the standard scheme for CZ gate. So everything you need, it's quite dense, but I guess it can be helpful for people who don't really know about neutral atoms in the first place, and they want to be able to contribute. Yeah. So thanks a lot. I hope that was helpful for you guys.
Yeah, no, that paper looks like it'll be a pretty good resource. I definitely put a link to that in chat as well. I was going to, so I want to encourage folks in chat to ask any other questions you might have for Loïc. We're getting some comments. Thank you for the awesome talk. Super interesting. So yeah, that's pretty great. I will maybe ask you a couple questions here while folks in chat are typing things. So let's go to the interview mode. So yeah, I think the first question I have is how did you get started in quantum computing in the first place?
Okay, that's a good question. So I did my engineering studies with physics and other stuff, but really quantum was the thing that was really interesting and the thing I understood the least, I guess. So that was quite intriguing. So that's why I went to a PhD in condensed matter physics, and then from then I think the rise of quantum computing over the last few years, I've done the rest. Like it's a very good time to be participating in the development of this new technology, either on the hardware side or software. It's a very good timing now.
Andrea from chat asks, when will the hardware be accessible?
That's great. Well, we're supposed to have it online for external users early in 2022. So yeah, let's get in touch if you want to implement something. So the access will not be free by default, unfortunately. So depending if there are some good projects that you'd like to run, let's discuss. But otherwise, yeah, you have to. It will be on we'll have a dedicated cloud offer.
Nice. Yeah, unfortunately, science development isn't always free. I know how much just even a single AWG costs.
Yeah.
So, yeah.
And we're not IBM. We cannot do that.
Yeah. I think that's an interesting precedent to set. So another question I had was, so you're kind of the lead of quantum software development at the company, and have obviously learned a lot of things along the way, both through your PhD and kind of working in industry and in the startup. If there was something you could go back in time and teach younger Loïc about, whether it be like something from physics or maybe a professional development skill or something like that, what would you want to make sure that you knew earlier on in your career?
That's a good question. I think quantum software requires some interdisciplinarity. So if you are a physicist, you should try to learn about open source development and code in general. And if it's the other way around, try to dig a little bit more into physics. Try to bridge the gap between the two fields. I would say that's really interesting. That's really important to do that early on.
So open source development is important.
Yeah.
Come hang out at Unitary Hack and learn how to do that. Maybe one other kind of follow-on question with that, like especially as a startup, why is open sourcing things kind of like a priority? Or normally we think of, if you're developing a new product or whatever, you want to keep it either like a trade secret or whatnot. Why did you make the decision to open source this, and what do you think the kind of benefits of that are?
Well, we believe that we are at a stage where our devices cannot already do something super useful right now in production and make people pay for it. So it's really important that we build a community, that we try to find use cases, that we try to understand how the devices work, to devise new protocols. And for that, open source is key, because then you can have more innovation and more people getting to work on that. So we are trying to contribute to that as a startup to make our developments accessible for everyone, because we know that we will benefit from it in the long run. The whole ecosystem will benefit from it, and it's the only way we can do something useful and in the long term, to try to have some common understanding of what is possible to do and how to do it.
Yeah, I think that makes a lot of sense. We might all be very soon approaching the start line for the quantum computing kind of like hardware development sort of thing. So yeah, I think I philosophically agree with that. Sweet. Well, we're pretty much at time here. I'm gonna do a little outro, well, in case people have any other questions. But yeah, so we've mentioned a few times Pulsar is one of the great sponsors of Unitary Hack. So you can find on their repo some issues that you might be able to help with. You can even get cash money for that if if you choose one of the bountied ones. So yeah, I'd strongly encourage you to, if you haven't tried open source contributions. I know sometimes it can kind of be scary, like there's a reputation of like the maintainers of the repo are gonna like yell at you or be mean, and I think I can pretty safely say Loïc and their team are really amazing to work with, so you don't have anything to worry about, as well as all the other projects that we have participating in Unitary Hack. So that's a great option. Yeah, also check out, we've got the links in the chat for the archive paper, for the docs. Yeah, and I'm excited to take a look. As I mentioned, I used to do a lot of automated laser control for actually nanodiamond stuff, and so I always like pulse design stuff. Sweet. Well, thank you so much again for joining us, Loïc. This is super fun.
Thank you very much.
Yeah. And for folks on YouTube, you'll find all the links that were in chat in the description below. So have a good one, everybody, and we'll see you on the Discord. Bye.